All right, so earlier we saw that any two 360-degree rotation loops are equivalent to each other. And the way we showed this earlier was by performing a homotopy between them, performing a gradual deformation from one 360-degree rotation to another. In particular, we did this by gradually shifting the axis of rotation. So for example, you can gradually shift from having this be your axis of rotation, the z-axis, to, I'm skipping some steps here, but eventually getting to the y-axis as your axis of rotation. And in this way, you can show that any two 360-degree rotation loops are equivalent to each other. So can we explicitly parameterize this homotopy using quaternions? So in order to do this, we're going to introduce a new variable t, which is going to range from 0 to 1. So as t goes from 0 to 1, the loop pt of theta will gradually deform from a 360-degree x rotation loop to a 360-degree y rotation loop. So we can kind of think of t as a deformation index. As t goes from 0 to 1, it indexes the stage in the deformation from the x rotation loop to the y rotation loop. So what is p0 going to look like? Well, that has to represent the x rotation loop. So it's literally going to be cosine of theta over 2 plus sine of theta over 2 times I, as theta goes from 0 to 2 pi. That's what p0 is going to be. Similarly, p1 of theta is a different loop. It's a y rotation loop, so it's given by this formula, cosine of theta over 2 plus sine of theta over 2j, as theta goes from 0 to 2 pi. But as this new deformation parameter, t, goes from 0 to 1, we have to transform this loop into this loop. We have to deform this loop into this loop somehow, algebraically. So how is that going to work? Well, before we write it out, let's just see what would pt of theta look like somewhere in the middle, when t is bigger than 0 and less than 1. So remember that the axis of rotation is gradually shifting. In the beginning, it's here. It's the x-axis. In the end, it's here. It's the y-axis. So let's write out some intermediate loop. So here's pt of theta, where it's about some intermediate axis. And I've just chosen an axis that's halfway between the x-axis and the y-axis. Namely, it's the axis x equals y. That's what I've drawn here. And here's my attempt to write out pt, the formula for that. I'm writing cosine of theta over 2 plus sine of theta over 2 times I plus j. Right? That's kind of, I'm trying to give the axis 1, 1, 0. So does this work? Well, we have a slight problem here, because what I've written is not quite a unit quaternion. This axis is not a unit, and therefore we don't end up with a unit quaternion. We can fix that pretty easily. I can add in these coefficients, root 2 over 2, root 2 over 2. Now it is a unit, and now this is a unit quaternion, and now this actually works. But that's not the only thing that's not the only possible intermediate thing I could write. This also works. I could write 1/2 and root 3 over 2 as my coefficients. Their square sum is still 1. This is still a unit vector. This is still a unit quaternion. So this is also a loop about some intermediate axis. And this is also a loop about some intermediate axis. So these are all different intermediate axes. Basically, the square sum has to be equal to 1 at every stage. All right. So let's now keep that in the back of our mind, and let's try and write a formula for pt of theta in terms of t. So let's just start from scratch. Okay, we need to give these following expressions at t equals 0 and t equals 1. We have to deform this expression into this expression as t goes from 0 up to 1. Okay, how can we possibly do that? Well, here's an attempt. Cosine of theta over 2 plus 1 minus t times sine of theta over 2i plus t times sine of theta over 2j. Well, I've introduced these scaling parameters t and 1 minus t. And why have I done that? Well, as t goes from 0 to 1, what's happening here? Well, when t is 0, this entire term vanishes, and this is equal to, when t is 0, this is just 1. So we end up with just sine of theta over 2i. We end up with exactly what we want here. Similarly, when t is equal to 1, what happens? When t is equal to 1, this is 0, so this vanishes, and we end up with just sine of theta over 2j. We end up with p1. Okay, so that's all good, but we still have an issue, the same issue as before. pt of theta is not going to be a unit quaternion for most values of theta, for most intermediate, for most values of theta. So at least when t is outside of, when t is not equal to 0 or 1. So we do still have a problem, but we can easily fix it. Remember that the sum, the square sum of this and this has to be equal to 1. Right now it's not quite equal to 1, but if we just stick on a square root sign, now it is equal to 1. The square sum of this and this is just equal to 1. It's 1 minus t plus t. So now this does work. And now we can feed this homotopy into Blender and allow Blender to enact it. All right, so we also looked earlier at a loop that does a 360-degree rotation about the x-axis, followed by another 360-degree rotation about the x-axis in the opposite direction. In other words, it does this, followed by this. So we already showed that that loop is trivial. We already enacted a homotopy that gradually deforms that loop to the stationary loop. But as an exercise, can you show this using can you show this using quaternions? Can you write down a quaternion homotopy that shows that this loop is trivial? So first, how do we write down this loop? Well, here's one way to write it. P0 of theta is equal to cosine of theta over 2 plus sine of theta over 2i for theta going from 0 to 2 pi. As theta goes from 0 to 2 pi, we're just performing this first part of the loop. Now, as theta goes from 2 pi to 4 pi, we perform the second part of the loop because we have a minus sign here. So now we're going in the opposite direction. And when theta reaches 4 pi, we're back to where we started. So that's how we can write down the loop. And do note that it's going from 0 to 4 pi now, not 2 pi. So earlier we performed that homotopy from this to the stationary loop. So as a challenge, can you write down an explicit homotopy, pt of theta, such that p0 of theta is given above, and p1 of theta is the stationary loop. It's just equal to 1. So as a challenge, can you try and write this down explicitly?